Let us begin with simple harmonic oscillators. A simple harmonic oscillator, or SHO for short, is a system where an object moves back and forth around a fixed equilibrium point. The most common examples include a swinging pendulum and a spring block system. For this video, we will use the example of a spring block system, where the restoring force is proportional to the displacement but acts in the opposite direction to make the block return to the equilibrium point, hence the negative sign. This is a simulation of a simple spring block system with no external forces. As the value of k increases, the spring becomes stiffer and the oscillations become faster. The angular frequency of the oscillator, which tells us how frequently the oscillations repeat, is given by under root k by m. Force can also be defined as the negative rate of change of potential with respect to position, which can be represented using this equation, where this operator, called del or nabla, is a gradient operator which is written like this when expanded. Since we are considering a 1D case, this is the only relevant term, since the oscillations are in one dimension. The force can therefore be written like this, and equating the earlier relation of minus kx, we get this equation, and on shifting the terms, and then integrating both sides, we then change the partial derivative to normal derivative since there is only one dimension, and we get the value of potential energy as half kx square. This is the graph of the potential energy, where the bottommost position is the mean position at x is equal to 0, and this corresponds to the stable equilibrium point in a spring block system, and the ends of the graph represent the amplitudes. The kinetic energy is given by half mv square, so the total energy is given as the sum of the potential and kinetic energies, or in this form where P is equal to mv. When we go down to quantum levels, this becomes a problem because according to the uncertainty principle, we cannot know both the position and momentum at the same time with absolute certainty. In a normal spring block system, if both P as well as X are equal to 0, then the total energy is 0. But this is not possible in quantum mechanics, so we use the time-independent Schrödinger equation to calculate the wave function of the system. Here, V of x is the potential, which can be replaced by half kx square. This integral can have many mathematically possible solutions, but to make them physically consistent, we use what is known as the normalization condition. To understand this, we represent the possibility of finding a system within any intervals as the integral of the product of the wave function with its complex conjugate. If the limits are set as minus infinity to infinity, this represents the probability of finding the system within the entire region of free space, and so this integral should be equal to 1, but in many cases it blows up to infinity, which is where the normalization condition is required. One such solution of the wave function is of this form, which represents a Gaussian curve. The final solution of the wave function is given by this equation, where h subscript n represents the Hermite polynomials. These are the first 5 Hermite polynomials. On solving for the value of energy at n is equal to 0, we get this equation where under root k by m is the angular frequency. So the energy at n is equal to 0, or the ground state energy, is given by this formula where h bar, the reduced Planck's constant, is a very small number but is not equal to 0. This is the equation for the energy in the nth excited state of the oscillator. Next up, we have the graphs of the wave functions for each value of n. This is important to find the probability of finding the system at any position, which is given by the square of the wave function. These wave functions have been plotted until n is equal to 4, but it can go up to any number. These are the graphs of the probability of finding the system at any position. The peaks represent the maximum probability of finding the system at those points. And if we look at the nodes, or these points, they represent the positions where the probability of finding the system is equal to 0. For psi 4, n is equal to 4 and there are 4 nodes. Similarly, if we take the example of psi 2, n is equal to 2, so therefore we have 2 nodes, or 2 positions where the probability of finding the system is 0. Some conclusions we can draw from this are that First, energy is quantized, which means it can only take certain values where n is an integer. And second, the oscillator can never have zero energy. The minimum possible energy is given by the ground state energy. Even though the quantum harmonic oscillator seems like a very specific problem, a block attached to a spring, it turns out to be a very important model in physics. Whenever a system is displaced slightly from its stable equilibrium, its motion can be approximated as a harmonic oscillator. Vibrating atoms in a crystal, oscillating molecules and atoms are some examples of these systems. The vibrations of molecules can be treated as quantum oscillators, helping us understand molecular spectra in detail. In solid materials, the collective vibrations of atoms are described using quantized oscillators called phonons. So, the quantum harmonic oscillator isn't just a mathematical problem, but it is a model that appears many times when we try to understand the microscopic universe.